Hello, and welcome to this Vivado quick take video, where we'll demonstrate features in System Generator for DSP that allow you to create a standard AXI4 Lite interface for a system generator model, and then export the model to the Vivado IP catalog for later inclusion in a design using IP Integrator. We'll also show how to use a processor to read and write to the AXI Lite interfaces via software. Design modules that are developed using System Generator usually form a subsystem of a larger DSP or video system. These system generator modules are typically data path heavy algorithmic models that are best created in a visually rich environment like MATLAB Simulink. The larger system is typically assembled with IP from the Vivado IP catalog. These IP typically use standard stream and control interfaces like AXI4 Lite, and the larger system is typically assembled using a tool like Vivado IP Integrator. Design creation and verification is exactly the same as any other system generator design that does not include an AXI Lite interface. Consider the FIR design shown here. Data arrives on the ADC in port as a 16-bit signed value with 14 bits of decimal notation. After passing through the FIR, bit growth increases the data to 22 bits signed with 19 bits of decimal. In the example, we want to be able to scale the output of the FIR to maximize the results in the envelope of the dynamic range allowed, so we multiply the result by a quasi-static constant from the power scale gateway in. After the scaling, we pass through blocks that allow us to change the decimal location and reduce the number of bits used to quantize the results. This gets passed to a block that squares the results to find the instantaneous power, and then tests for a maximum and local maximum value, which we could use to determine subsequent power scale factors. Since we don't expect the maximum power to change frequently, we might use the ARM processor in Xilinx's Zinc all-programmable device to compute and even predict new power scale values via software. The data that is needed to be read by the processor is located at the max power gateway out, and the power scale gateway in should be updated by the processor. To accomplish this, we need to convert the gateways from simple ports to AXI Lite register locations. Selecting the max power gateway, we see interface options under the Implementation tab. We can change the type from None, which represents a simple bus, to AXI4 Lite, which will convert the port to a register accessible to the processor. We'll do the same at the power scale input gateway, but we notice that the sample period for the interface is 491.52 MHz, too fast for the processor and AXI infrastructure. So we'll lower the sample period to 1/8. This requires the addition of an upsample block immediately after the gateway, so the entire data path runs at full speed. We also add a downsample block prior to max power. Simulating the design shows we get the proper frequency response. We can now compile a model for inclusion in the Vivado IP catalog. We change the compilation type in the system generator token from HDL netlist to IP catalog. In the optional settings, we can specify vendor, library, version, category, and status. We should also change the part to match the ZC706 evaluation platform and set the output target directory as appropriate. After compilation, the system design is ready to be used with Vivado. We'll start by creating a new project for the ZC706 evaluation board. Next, we add the IP to the user IP repository. We create a new block design and add the IP by searching for it. Notice that the ADC in and DAC out ports are shown as simple buses on the IP, and the max power and power scale gateways exist as registers accessible through the S-AXI AXI4 Lite interface. Vivado is board aware, and since we want to run the FIR at a high clock frequency, we'll move the differential clock interface on the board part interfaces tab from the unconnected to connected interfaces. We'll configure the output clock to be 491.52 MHz. The final IP to add is the Zinc processing system, which gets configured with block automation to apply the board presets with locations for the DDR, peripheral interfaces, and other settings specific to the ZC706. Connection automation allows us to easily connect the AXI4 Lite interface on the IP to the Zinc processing system, and since the IP has a single clock, we want to use the 491.52 MHz clock for the system connections. Testing of the IP and system can be accomplished by adding a direct digital synthesizer. Its clock gets connected to the system clock, and the IP gets customized. The system clock rate is changed to match our requirements, and the implementation details are changed to output only the sine waveform. We can set a frequency in the Output Frequencies tab, and by selecting the Summary tab, we note that the output width is currently using 8 bits. By setting the spurious free dynamic range to 96 dB, which is an estimate of 6 dB per bit, we can utilize 16 bits for the output to match the IP. The data portion of the DDS is connected to the ADC in port of the IP, and we can mark the signal for easy inclusion as a debug probe. Since I don't wish to drive the output of the FIR to the actual board, we can add a reduction block to the DAC out port and mark that signal for debug 2. After synthesis, we'll set up the logic analyzers by running the tools setup debug command. The board resets are the final automated connections, and verifying the design shows no issues found. We create the HDL wrapper for the source and start synthesis, followed by exporting the hardware system to the software development kit. The hardware platform specification is added to SDK, and we can start a new application project. If necessary, we add the drivers to the project as a local repository. The documentation for the IP shows 4 commands available. The first command will initialize the IP's instance pointer, so we can use it with other commands and have a unique instance when multiple versions of the IP exist. After setting the proper include files, we can finalize the parameters in the function call by adding the device ID from the xparameters.h file. The next command writes a value into the register for power scale. Because the port was 16 bits unsigned with 8 bits of decimal precision, setting it to the value 256 represents writing a 1 to this register. The read function also exists for this register, which we can use to verify that the data was written and set properly. Viewing the logic analyzers after downloading the bitstream shows there is data entering the FIR, but not leaving it. This is because the software has not been executed yet, and the default value for power scale is 0, thereby scaling the output to 0. Executing the software shows the correct value of power scale, and also that the IP is now actively implementing the design. By converting standard gateway ports to AXI4 Lite interfaces, We can extend the capabilities of System Generator into generating IP suitable for inclusion with processors. It is easy to migrate current System Generator designs to the IP catalog. Changing the interface type on gateways makes those ports accessible from a processor. Building a functionally correct all-programmable system is quickly done by the use of the board interface, connection, and block automations with an IP integrator. And all software APIs and documentation are easily accessible within the Software Development Kit to allow software engineers quick integration of the DSP system. System Generator for DSP makes it easy for you to take your DSP-centric data path portion of the design and use it as part of your all-programmable embedded hardware and software system. Thank you for watching this Vivado Quick Take video. Look for other videos in this series, including moving the AXI4 Lite interface to a different clock domain, and also advanced techniques for working with multiple clock domains in IP Integrator.